Hello friends, welcome to Emotional Impulse. So as I said earlier that today I will start some inquiry about DNA. Those questions are related with DNA, some basic questions are related with DNA. So from previous class we got one knowledge, one information about DNA, that the length in between two DNA helix of one molecule of DNA is 20 degree angstrom. But the question is why the length is 20 degree angstrom? So the answer is the length is 20 degree angstrom because the hydrogen length in between two nitrogen base is 20 degree angstrom. Means when adenine is going to connect with the thymine and the guanine is going to connect with cytosine, the length of the hydrogen bond means the adenine connected with thymine with 2 hydrogen bond and guanine connected with cytosine with 3 hydrogen bond. So the length of the hydrogen bond is 20 degree angstrom. Okay, this much length. That's why it is known as 20 degree angstrom length in between two helix of one molecule of DNA. So this is the reason, because the length of hydrogen bond is 20 degree angstrom. So this is the answer. And the second question is why the it is there that purine always connect with pyrimidine always connect with purine. Why? Because if one purine molecules or one purine base pair with connect with another purine base pair, the length of this base pair will be increased rather than the 20 degree angstrom. Okay, so if the bonding will be purine with purine, the length will be increased, and if the bond will be pyrimidine with pyrimidine, the length will be decreased, but from 20 degree angstrom. So that is the reason. And the third question is why the DNA is showing anti-parallel manners all the time. Why? Anti-parallel manners because if you see the structure of pentose sugar, there are 5 carbon is there, 1, 2, 3, 4, 5. So there is always tendency to each of every nitrogen connect with the 1 number carbon. Okay, so this is the pentose sugar structure. This is the 1 number carbon. If adenine will be there, this adenine will connect with this 1 number carbon. Okay, but if this type of structure is remaining there, so this side thymine will not find out the 1 number carbon. They will find out 1, 2, 3, 4 number carbon. Okay, so that's why the right-handed pentose sugar will turn itself upside down. Okay, so this is the normal. Okay, I am showing with my hand because today I will discuss some another topics. That's why these are the question. That's why I am showing like that. If you want, then I will discuss again in my next video. So suppose assume these are the structures of pentose sugar. This is 1, 2, 3, 4 and 5 number carbon position. Okay, so like this type of carbon, like this type of pentose sugar will be present, this type means this type of manners will be present in this side. So that side thymine will add with the 1, 2, 3, 4 number carbon. Okay, but this thymine need 1 number carbon of the pentose sugar. That's why this pentose sugar invert its position upside down. Okay, and that's why this thymine will find out the 1 number carbon of the next pentose sugar. Okay, so that's why one is normal and one is upside down, and that's why they are showing the anti-parallel manners of the DNA. Okay, so these are the thing. Okay, and the next question, why DNA is negative in nature, or you can say the hydrophilic in nature? Nothing, this is a simple reason, just because of pentose sugar with the hydroxyl end. Okay, so this pentose sugar connect with the phosphate, so phosphate and pentose sugar is there. So phosphate means PO4, and then here is the pentose sugar connect with phosphate. Okay, so this phosphate and this oxygen, this hydroxyl radicals is there. That's why it is showing the negative manners. Okay, so just because of pentose sugar connect with phosphate, that's why it is showing the normal negative in nature, and that's why it is hydrophilic in nature. Okay, means their OH minus ions are there or radicals there, so there is a tendency to connect with water. Okay, so this is the polarity, that's why it is hydrophilic in nature. These are the reason. Okay, so these are some basic questions, those are related to DNA today I discussed. Now the main topics of my or your or our today's lesson is DNA packaging. Okay, so what is DNA packaging? So if you want to remember, okay, if you try to remember that my previous class lessons that I discussed earlier, that there is one question, there is some inquiry, that is that DNA molecule, some proteins was there. Okay, what Misher did, Misher find out one molecules, that is histone protein, protamine, these are there, no? So in DNA molecules some proteins are there. So you can say that for discussion about this type of topics we have to go back in my previous classes. Okay, so let's come back to the previous classes. Okay, so just think about one cell. Okay, one cell is there, into the cell one nucleus is there, into the nucleus chromosome is there, means chromatins are there. So there are two types of chromatin. Okay, one is heterochromatin, another is euchromatin. So it is revealed that the heterochromatin is a little bit of dense. Okay, so it's heterochromatin, normally iron is there. On euchromatin, that is transcriptionally active, means this type of chromatin will show the transcription. Okay, it will participate in transcription process. So these are known as the euchromatin. So in euchromatin normally DNA are there. Okay, so in chromosome, if I will say, there are some kinds of protein also there. So if I will say what kind of chemical components are there in the chromosome. So chromosome contain various kind of chemical component. First one is DNA, RNA, proteins, some kinds of ion. What kind of nucleic acid? DNA and RNA. What kind of proteins? Histone proteins and non-histone proteins. Okay, and what kind of ion? Magnesium ion, calcium ions are there. Okay, so if I will say how many percentage of DNA are there in chromosome, how many percentage of RNA are there in chromosome? 90% DNA is there in chromosome and only 10% RNA. Okay, so DNA, RNA are there, protein are there. So you can say the histone proteins, and you can say the non-histone chromosomal protein. So non-histone chromosomal protein, shortly it is saying that NHCP, non-histone chromosomal protein. Okay, so we got some information about chromosome. Okay, so now how does one DNA molecule can connect with one histone protein? Proteins are there, DNA are there, but what is the relation in between protein and DNA? In DNA, nucleic acid also there. Okay, we know about their arrangement, about the nucleic acid arrangement, about the nitrogen base pair arrangement, about the pentose sugar arrangement, about the phosphate backbone arrangement. Okay, we know everything. Just because of phosphate backbone or sugar molecule, the DNA is showing the negative in nature, hydrophilic in nature, we know everything. But we don't know one thing: how does one molecule of DNA can wrap around the histone protein? By the process of DNA packaging. This is our today's lesson. Okay, this is packaging of DNA helix with protein. That is what kind of protein? That is histone protein. Okay, so before entering in this packaging, we have to know about some kinds of protein in our DNA. We said already histone protein and non-histone proteins, but we will discuss only the histone proteins. Histone proteins, one kind of alkaline protein. Okay, and in our body there are four types of histone protein. Okay, H2A, H2B, H3 and H4. Okay, so what kind of histone proteins? H2A, H2B, H3 and H4. Four types of histone proteins are there in our body. These are the thing. And DNA molecules will wrap around these histone proteins. Normal, clear. But one thing, these histone proteins will not remain like that. Each of every histone proteins will form another one like that by itself. Okay, means these histone proteins will make another H2A, H2B, from H3, H4. So now look very carefully. Look here, one H2A are going to make another H2A. So two H2A. Here one H2B going to make another H2B. So two H2B, H3, H3, H4 again forming the H4. So here 1, 2, 3, 4, 5, 6, 7, 8. 8 molecules of histone proteins are there. So when from 4 molecules of histone proteins, another 4 molecules of same kind of histone proteins are forming and they are remaining in the same position. So total 8. Okay, we are counting and we are getting 8 number of histone proteins molecules. So this total histone proteins will count like 8 histone proteins. This total 8 histone proteins is known as histone octamer. and these histone proteins always remain in octamer form. Okay, and one DNA molecules is going to wrap around this octamer of the histone proteins. Okay, so this is the thing. So in our body, DNA molecules are going to wrap around the histone octamer and again forming the another wrapping. So this is the normal DNA chain is coming, wrapping one histone proteins octamer, again going wrapping. So in between two histone proteins octamer where the DNA is wrapping around, okay, behaving like that, gap is there, and this gap will be fulfilled by one DNA molecule that is known as linker DNA. Okay, so let's come back to the discussion first. Suppose this is one cell, this is the nuclear membrane, this is the chromosome. Okay, so from this chromosome, okay, I collect one chromosome. Okay, look, this is one chromosome structure, and this is the chromatin fiber. Chromatin fiber is going, and here this chromatin fiber, one nucleotide chain occur, and when this nucleotide chains are arranging here, this round, red color round, this position is known as histone octamer position. Look very carefully. Okay, look here, 1 2 3 4 5 6 7 8 molecules are there. That means H2, H3, H4, and H2A, H2B, H3, and H4. This type of 4 molecules divided again. So 2 H2A, 2 H2B, 2 H3, and 2 H4, like that 8 molecules are there. That's why it is known as histone octamer. But when in this histone octamer, or you can say that surrounding this histone octamer, DNA molecules are there, this total structure. Okay, so DNA molecules wrapped histone octamer is known as nucleosome. Okay, so this is nucleosome because this is histone octamer but wrapped with the DNA molecules. So here one histone octamer, here one histone octamer, and you can say that this is nucleosome. So now it's becoming nucleosome, but in between two nucleosome, one gap is there, I said already, and this gap will be fulfilled with one DNA that is known as linker DNA. So that means they are forming the link in between two nucleosomes. This is the linker DNA, and by this way they are forming the DNA helix. So DNA helix are there. These are the bonding. Okay, here phosphate backbones are there, and their nitrogen base are there. So these are the nucleotide, or you can say the nucleotide polymer or nucleic acid, anything. But this nucleic acid, in this nucleic acid, proteins are also there. Okay, but protein will remain like that, and this protein will attach with the hydroxyl radical. Okay, from the phosphate molecule is coming, hydroxyl radical of phosphate molecule, it will attach in that position. Okay, so this protein is alkaline in nature, and this alkaline protein will act with the phosphate hydroxyl radical. Okay, and that will form the nucleosome structure. And in this structure, it is saying this structure is known as bed on string structure, like that, because here one nucleosome, here one nucleosome. Okay, so this type of structure is known as a string on bed, or like the structure it is saying. So in today's class we got one information about DNA, that how does one DNA molecules can wrap around the protein molecules, that is known as histone proteins molecules, and these wrapped histone proteins molecules with DNA is known as nucleosome. Okay, so hope students or friend you like my video. So in next topics we'll discuss about the transcription of mRNA, or how can one mRNA form from the DNA molecules. Okay, from this process I discussed already, that was the central dogma process. Okay, so next video we'll discuss about the transcription process. So till then, take care, bye bye, and subscribe my channel.
Audio Jungle. Audio Jungle.